Meet CODECO's Synthetic Data Generator, a powerful tool to create realistic, time series workload data for edge cloud environments. This tool is specifically designed to facilitate testing, benchmarking, and foster innovation. While data pours in from domains like healthcare, finance, and manufacturing, what is missing is the foundational data needed to understand how workloads behave across distributed, hybrid computing environments. There's a critical and often overlooked gap in the data landscape: a lack of real, representative workload data generated by edge cloud continuum infrastructures. And this isn't a minor inconvenience, it's a serious roadblock. The absence of real, representative workload data leaves data analysts, researchers, and system architects unable to simulate real-world conditions, test algorithms, or fine-tune orchestration strategies. Without access to accurate, workload-specific benchmarks, it's nearly impossible to build robust, scalable, data-driven solutions. These solutions are essential for coordinating edge nodes, optimizing resources on the fly, and enabling proactive adaptation in dynamic, decentralized environments. The result? Progress stalls, innovation slows, and the full promise of edge intelligence, ultra-responsive, context-aware systems, remains frustratingly out of reach. If we want to realize the future of truly intelligent edge computing, bridging this data gap isn't optional. It's urgent. Addressing this gap requires more than just collecting more data. It demands a smarter way to generate it. That's where CODECO's Synthetic Data Generator comes in. This asset's purpose is to simulate workload data in time series across the edge cloud continuum. CODECO Synthetic Data Generator doesn't just fabricate numbers, it models behavior. It captures the complexity of real-world systems by generating data that mirrors the dynamics of actual workloads. How? This is achieved by integrating insights across three crucial dimensions. First, infrastructure metrics, from CPU utilization and memory pressure to energy consumption, all derived from real system performance data. Second, network behavior, including ingress and egress bandwidth, link failures, and both overlay and underlay network characteristics. And third, the data-centric layer, metrics like data freshness, portability, and compliance with regulatory standards such as GDPR. CODECO blends real monitoring traces with custom built-in formulas designed to approximate the metrics that traditional systems can't capture by default. The result? Synthetic datasets that are not only realistic but also reliable, giving analysts the tools they need to test, optimize, and innovate with confidence. This empowers analysts and researchers to confidently test, optimize, and innovate. CODECO's Synthetic Data Generator fills the critical data gap in the edge cloud continuum. It offers a rich, structured dataset, enabling scientists to truly understand and fine-tune the behavior of complex cloud edge ecosystems. And more importantly, it shifts the paradigm. With CODECO's Synthetic Data Generator, the focus shifts from merely reacting to issues after they occur to anticipating and proactively adapting to them. It's about anticipating them, proactively adapting, enhancing orchestration, and unlocking the full potential of edge intelligence with clarity, precision, and foresight. Now, let's take a closer look at the architecture in action. CODECO's Synthetic Data Generator is deployed on top of a Kubernetes cluster, no matter how many nodes are involved. In addition to Kubernetes, it also requires Prometheus, the open-source monitoring system that collects performance data from across the cluster. CODECO's Synthetic Data Generator is designed to simulate rich, cross-layered metrics generated by its three core components: ACM, responsible for automated cluster management; MDM, which provides metadata about the cluster; and NetMe, focused on managing and monitoring network-related behavior. At its core, it has two key subcomponents. First, the collector. This module captures real-time metrics that are scraped directly by Prometheus from across the Kubernetes cluster. Second, the synthesizer. This is where the real transformation happens. The synthesizer creates new, meaningful synthetic metrics by combining existing data from the Prometheus monitoring tool, which provides low-level system metrics directly from each node's kernel. Using custom-built formulas, the synthesizer generates realistic, feature-rich time series data that goes beyond what's available by default. Together, these components allow us to simulate complex system behavior, enabling deeper insights into how edge cloud infrastructures perform under real-world conditions. Now let's walk through the installation steps for deploying CODECO's Synthetic Data Generator, whether you're using a Kind cluster or a bare metal Kubernetes setup. Before you begin, make sure the following are in place: a working Kubernetes cluster, regardless of the number of nodes; admin access with permissions to the default service account; Python installed, preferably version 3.10 or above. Before installing, Prometheus must be installed in your cluster. If it is not, then run the following commands as shown. After all the pods are in the running state, now you should have Prometheus installed in your cluster. For Synthetic Data Generator, you'll need to clone the official repository. This repository contains everything you need: the controller definitions, deployment scripts, and the data extractor to generate the synthetic datasets. Therefore, run the command shown on the screen. Once cloned, navigate into the directory to access the files needed for setup and execution, and change the branch to version 1. As shown, CODECO's SDG architecture uses three main controllers: ACM, MDM, and NetMe, each designed to simulate a specific layer of the Edge Cloud ecosystem. The corresponding documentation in the repository also provides the full installation and execution steps. Before installing the controllers, you'll need to define your cluster's topology. In simple terms, the topology describes how the nodes in your cluster are connected to each other, kind of like a map showing which nodes can communicate or interact. This information is essential for the NetMe controller to simulate network behavior accurately, and it must be defined before deployment. To define the topology, find the YAML file named as netma controller deployment in the path shown right now inside of the repository. After you find it, search for a field named as topology.json and provide your own topology. This field outlines which nodes are connected using an adjacency matrix. Once you've set up your topology, execute the commands shown to deploy the synthetic controller. After deploying and running the controllers, it is possible to proceed and collect results using CSDG's extractor. In order to gather results by the executed controllers of the CSDG, navigate to the data extractor directory as shown and install the needed Python dependencies for the extractor script. You can run it in two modes: write or append. Use the write mode the first time to create a new dataset file from scratch. Then, use the append mode when you already have a dataset file to add new records to the same file without losing previous data. Here is an example of how to execute the extractor script using the write mode. You can stop the script by pressing Ctrl and C on your keyboard. The script is made for Python 3.10, but it works with other versions too. Just know that some dependencies may differ. And that's it. Your synthetic dataset is ready to fuel analysis, benchmarking, or AI-driven modeling across your edge cloud ecosystem. With the CODECO extractor executed successfully, the final result is a structured and comprehensive dataset stored in a file named data.csv. This dataset is a rich compilation of time series metrics that reflect the behavior of your Kubernetes-based edge cloud infrastructure. Inside, you'll find cross-layered data points generated by the ACM, MDM, and NetMake controllers. This dataset encompasses a wide range of metrics, including CPU and memory usage, network conditions such as link failures and bandwidth, and higher-level indicators such as data freshness, compliance, and energy consumption. Each row in the dataset represents a snapshot in time, a blend of real metrics captured by Prometheus and synthetic values computed by CODECO's custom formulas. This output isn't just numbers, it's insight. It allows data scientists, researchers, and engineers to test algorithms, benchmark systems, and proactively study behavior, long before any critical failure ever occurs. With this data in hand, you're equipped to explore, analyze, and optimize the edge cloud continuum like never before. Now that you've got your synthetic dataset, it's time to put it to work. Here are 2 exercises to help you explore the power of CODECO's Synthetic Data Generator output and gain hands-on experience with predictive modeling and data analysis. Exercise 1. Predict energy consumption with ML/DL models. In this exercise, you'll use the generated dataset to build a model that predicts energy consumption at the node level for all the nodes participating in the cluster. Start by selecting all the features, such as CPU usage, memory load, network activity, and data-related metrics. Alternatively, exploit feature importance methods like principal component analysis to reduce the dimension of the dataset's features and train the model only with the most important ones. Then split your data into training and testing sets. You can begin with traditional machine learning models like linear regression, random forest, or XGBoost, and then move on to more advanced deep learning architectures like LSTM, GRU, or even transformer-based time series models. Compare model performance using metrics like MAE, RMSE, and R-square score to evaluate how well each approach predicts energy usage under different workload patterns. The goal is to identify patterns, learn behaviors, and forecast energy trends, just like you would in a real cloud edge monitoring environment. Exercise 2. Discover behavioral patterns through clustering. In this exercise, you'll use clustering techniques to uncover hidden behavioral patterns in your edge cloud infrastructure without needing any labels in advance. Clustering helps you group similar system states together, whether they represent high load, idle behavior, network congestion, or potential anomalies. Start by selecting relevant features from your dataset. For example, CPU usage, memory usage, ingress and egress bandwidth, or node energy consumption. Clean and normalize the features to ensure they're on a similar scale. This is critical for effective clustering. Use a clustering algorithm like k-means, dbScan, or hierarchical clustering. Use the elbow method for k-means to decide on the number of clusters and let the algorithm assign cluster labels to each data point. Then, interpret the clusters. The most important part of this process is providing context for each cluster. Use cluster profiling to calculate the average of each feature within every cluster. This helps you understand the typical behavior of each group. As an example, one cluster could have high CPU and energy usage, thus meaning that it is in a high loading state. Use box plots, bar charts, or radar plots to compare how each feature behaves across clusters. Use PCA or TSNE to reduce dimensionality and visualize clusters in 2 dimensions. This helps you to spot outliers or overlaps. Based on your profiling, assign names to clusters like energy-efficient operation or failure-prone period. These human-readable labels make the insights actionable for operations and orchestration. The goal isn't just to group data, it's to discover meaningful behavioral states of your edge cloud system. Clustering helps reveal patterns you might miss with manual inspection, making it a powerful tool for adaptive orchestration, proactive scaling, or early anomaly detection. With CODECO's Synthetic Data Generator, you don't wait for real-world data. You generate it, simulate, analyze, and optimize all before deployment. The future of edge intelligence starts here.